Hello, Integrated Math 1. Welcome to lesson 3.1.1b. We're doing day 2 of our geometric sequences and exponential functions. And we were doing a really awesome job of it. You guys were killing it last time. So let's see what we can do today. Last lesson was the big lesson. We just have a little bit that we need to cover today because we have a key term that we need to talk about. So we learned last time that we could take our geometric sequences and we could take that explicit geometric formula, we could turn it into an exponential function. Today, we're going to push it a little further and we're going to look at something called a horizontal asymptote. No, I'm not swearing at you. That's a legitimate math word. So just a reminder, last time we said that we were able to take our lovely geometric sequences, right, where we had our explicit formula, our formula was equal to the first term times the common ratio to the n minus 1 power. But we're moving away from this and we're heading toward writing as an exponential function where f of x equals a times b to the x. And if you recall last time, we discovered that it was actually really easy to write these because a is our y-intercept. Also, it's where x equals 0, right? Always useful. And of course, b is our constant ratio or common ratio, whichever way you want to call it. Both ways of saying it are correct. So it was really nice because if I have my y-intercept and I know what my constant ratio is, boom, I could write the exponential function. Very convenient, very, very useful. So we are kind of moving away from this form and we're moving more toward this lovely form over here. And we talked about how to do that last time. So let's take a closer look at these graphs and tables. So you've explored output values with integer and rational exponents for the exponential function f of x equals 2 to the x power, right? We did 2 to the 1 power, 2 to the 2 power, 2 to the 3 power, 2 to the 4 power, on and on. We even did 2 to the 0 power, right? We said anything to the 0 power is 1. But what happens if you have a negative exponent? We've talked about this in both the past. We've talked about negative exponents before. So here's what I would like you to do. Here you have f of x equals 2 to the x power. And you know if we plug in a 0, 2 to the 0 power, anything to the 0 power is 1. So what if you plug in a negative 1, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4? Work that out. I actually started with the negative 4, but work that out. Hit pause to work this out and fill in your table, and then hit play when you're ready to check your work. So. I'm going to start with this end over here. So 2 to the negative 4 power. We don't like negative exponents, so I'm going to rewrite this as 1 over 2 to the 4th power, and I know that 2 to the 4th power is 16. 2 times 2 times 2 times 2. So I get 1 over 16. If I plug in a negative 3, 2 to the negative 3 power, that's 1 over 2 cubed, so 1 over 8, 2 times 2 times 2. 2 to the negative 2 power is 1 over 2 to the 2nd power, or 1 over 4. And of course, negative 1, 2 to the negative 1 power is just 1 over 2 to the 1 power, which is just 1/2. So as we move backwards, so last time we moved forward, right? 2 to the 0 power, 2 to the 1 power, 2 to the 2 power, on and on and on. We noticed it was getting bigger and bigger. But what happens when I move to the other side of my graph? What happens with these negative exponents? What's happening is something called a horizontal asymptote. Sorry about the noise outside. They're doing some work out there. A horizontal asymptote is a horizontal line that a function gets closer and closer and closer and closer to, but never actually intersects it. Never actually gets there. So it gets really, really, really close, but it never actually touches the line. It never gets there. It just gets super, super close. So consider the table of values you just completed. How does f of x change as x approaches negative infinity? How does my function, what does it look like my function is heading toward or getting closer toward as x gets smaller and smaller and smaller, right? As I negative 1, negative 2, negative 3, negative 4. As I head toward negative infinity on my x, look at these values we did for f of x or y. What does it look like my function is heading toward? My output is heading toward, as if I were to move further and further and further this way. Go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to check your work. So I notice I went from 1 to a half, which is smaller than 1, to 1/4, which is even smaller than 1, to 1/8, which is even smaller than a fourth, to 1/16, which is even smaller than an eighth. As x gets to approaches negative infinity, as x goes more and more and more negative, I can see that f of x is getting smaller and smaller and smaller and smaller. It's getting closer and closer and closer to 0. It never actually gets there, but it gets closer and closer and closer and closer to it. It's trying really hard to get there. It never actually gets there, but it's trying really, really hard. It's pushing it closer and closer. So with that in mind, I actually have 3 functions here. I have a function, and a function. Which one of these is 2 to the x power? See if you can figure out what 2 to the x power is, and then we're going to identify that horizontal asymptote. So go ahead and hit pause, figure out which function it is, and then hit play when you're ready to keep the party going. So the way I found this, I kind of used the table a little bit, and I plugged in that -1, right? We did that earlier, right? We plugged in a -1. We got 2 to the -1. We said that was 1/2. So I know we did that on the table. You don't have to rewrite that. But I know that means that if I plug in a -1, I get an output of 1/2. So my x coordinate is -1, but my output is 1/2, which is right there. Ooh, there we go. It's right there. You see how that's 0.5? That's a half. Great. So that means it's got to be this top function, doesn't it? That means that f of x is this top function right here because it hits that point. Yay, good stuff. Let's talk about the horizontal asymptote for a minute. We said it was approaching 0. And you can see as I move to the left, it's getting closer and closer to 0. Now, it doesn't actually touch 0, but it gets really close to it. So this is where y equals 0, right? It's getting really close. Y never actually gets to 0, but my y coordinate's getting really close to 0. It just never actually gets there. So we're going to say that the horizontal asymptote is y equals 0. Because y never actually gets to 0, but man, we get close. So that y value gets smaller and smaller and smaller and smaller, almost to 0. So we're going to say the horizontal asymptote is at y equals 0. Now, you will notice there are 2 other functions here, right? I've got the slightly paler green one and then the really pale green one. Yeah, this is on page 19 in your workbook, by the way. So my other 2 functions are 3 to the x power and 4 to the x power. They're also here. So which is which? Can you just real quick identify for me which function is which function and how you know that? Hit pause to work that out. Hit play when you're ready to check your work. So let's talk about 3 to the x power. Remember how last time I plugged in a -1 and I was like, that's where it should hit. So I'm going to do that here. If I plug a -1, that's 3 to the -1 power, which is 1/3. So if I plug in it, right, if I do 3 to the -1, I get 1/3. So that means if I plug in a -1, I get a 1/3 out of it, right? Oh, that's a G. I put F's. That's a G. G. My bad. I'll fix it later. So that means it should go through the point -1, 1/3. So here's -1, and not all the way to a half. We're just going to a third. I believe that puts it right about there. That's about a third of the way. Yeah. So it looks like this middle line is going to be our g of x. Sorry, that's an F. I should say g of x. My bad. So it looks like that middle line there is going to be our g of x, 3 to the x power. And I'll do the same thing here for 4 to the x power. I'm going to plug in, right? So it's an h of, I'm going to plug in a -1, see where we end up. So 4 to the -1, I know that's 1/4. So if I plug in a -1, I get an output of 1/4. So that means if I go over -1, I'm only going to go up to a fourth, which is half of a half. So let me get here. So it looks like this bottom guy, and again, that should be an h. Sorry about that. That bottom guy is going to be my h of x, or 4 to the x power. Sorry about my j's and h's and f's. My bad. I will fix later. So we said this is top one is 2 to the x, the middle one is 3 to the x, and the bottom one is 4 to the x. Hopefully you're seeing some patterns here. What are the horizontal asymptotes for g of x and h of x? And how does that compare with the horizontal asymptote for f of x? Hit pause, jot down your thoughts, hit play when you're ready to check your work. So I was looking at this and I realized, remember how we said that as you plug in more and more negative numbers for 2, it got closer and closer to 0 for y. So we said the horizontal asymptote was y of x. It looks like that's also happening for 3 to the x, and it's also happening for 4 to the x power. They're all doing it, aren't they? As I plug in more and more negative numbers, I get closer and closer to getting that output of 0, get closer and closer to y being 0, but I never actually get there. So it looks like all of the functions have the same horizontal asymptote. All of these functions have a horizontal asymptote at y equals 0. So can you look at how each of the three functions approach that horizontal asymptote? What's the same? What's different? Just jot down your thoughts. Hit pause, write it down, hit play, keep going. So I noticed that 2 to the x power didn't get there as fast as 3 to the x power, that 3 to the x power headed toward that asymptote faster. I also noticed that 4 to the x power has headed toward that asymptote even faster, didn't it? So while they all have the same asymptote, the greater b value, the greater base of your exponential, the more quickly it's approaching that asymptote from the right to the left. It's dropping down toward it a lot faster, isn't it? So it's interesting to note. As always, guys, hope you found this helpful. I hope you found this useful, and I'll see you guys later. Let me know if you got any questions. Talk to you later. Bye.